Hello friends, in section 10.2 we are going to cover congruent chords. So we are going to apply relationships between congruent chords of a circle. And to start, we have two theorems to discuss. So the first one is theorem 77, which states that if two chords of a circle are equidistant from the center, then they are congruent. So if we knew that segment GB was congruent to segment BF, that is telling us they are equidistant. Again, we are always measuring distance in a perpendicular fashion. Okay? So if I knew they were equidistant, then I can conclude that the chords are congruent. Chord CE and chord, we call that C prime and E prime. And our second theorem is the converse of that. If the chords are congruent, so segment C prime, E prime is congruent to segment CE, then I can conclude that they are equidistant from the center, or segment BG is congruent to segment BF. Those are the first two theorems. I want you to see if you can use that to make some conclusions in example 1. Go ahead and press pause and see if you can use that to conclude anything about X. So we see that the chords are congruent, so we can conclude that the chords are equidistant from the center, and so X is equal to 16. Example 2 is a little bit trickier, but I want you guys to label the things that you've been given and press pause. See if you can determine what the radius of circle O is. So I'm starting with these facts. I know that PQ is 30 and that the segment BO, our radius, is perpendicular to the chord PQ, which allows me to conclude that that chord has been bisected, and that's from our section 10.1 notes. From here, I don't know segment CO or segment OC, and I need to find the radius. What I need to do here in that case is draw in a new chord or a new radius. And note, I have now created a right triangle. And while I know one side or one leg is a length of 15, and I know the hypotenuse is my radius, I'm still missing segment OC. And while I'm missing segment OC, I do know that segment BO is going to be congruent to segment QO. And if segment QO is the radius and segment BO is also a radius, I can write that segment OC is the radius minus 5. And now I have my right triangle that I can use the Pythagorean theorem to solve. I have a leg of r minus 5 that I'm squaring, plus my other leg, which is a length of 15 that I'm squaring, and I can set that equal to the hypotenuse, which is my radius, squared. Now I've got to solve an algebra problem. In this case, I do get r squared on both sides of this equal sign. When I subtract r squared from both sides, those will go away. Be careful with your algebra here. That doesn't mean I can randomly move this equal sign. On the right side of my equal sign, I have nothing left. I need to put a 0 in there. And I have a negative 10r, a plus 250 when I combine my like terms. And so that equals 0 is very important. I can complete this problem and find that the radius is equal to 25. All right, the last thing I want us to be able to do in section 10.2 is a proof. So go ahead and maybe press pause, see what conclusions you can make, and see if you can find a way to prove that triangle PQR here is isosceles. We'll slowly unveil some of this proof. First, the fact that I have an isosceles triangle tells me that segment BA is congruent to segment BC, and those are congruent chords. BA and BC are chords of this circle. That should be helpful. Next, my other three givens give me the information to conclude that segment PQ must be congruent to segment PR. The fact that they're perpendicular tells me that they are the distance from the center P. I know P is the center because it's named circle P. So I need all three of these to be able to make that last conclusion here. That's enough information. Now I have segment PR congruent to segment PQ. Therefore, my triangle PQR must be isosceles. Because congruent legs implies an isosceles triangle.